Today we're going to be talking about accuracy and how significant digits help us communicate accuracy. So let's get started. Now, if I were trying to measure the distance between here and Banff, it doesn't make much sense for me to be using a meter stick. That's the first thing. We got to think about the right tool to measure. It would be smarter to measure in kilometers and use a different tool than to use a meter stick and actually count out all the meters between here and Banff. It just doesn't make sense. All right. The second thing that we need to consider is we need to consider how accurate of a tool we have, and the accuracy of the tool determines how many significant digits we represent. Now, this will all make sense in a second when we start doing examples, but I wanted to show you something here. I'm going to show you the top-down camera here. So here we go. Boom. Boom. There we go. Nope. Boom. Here we go. Beautiful. All right, so I want to show you the top-down camera there, and what I want to do is I want to show you my wallet. So here's my wallet. If I take my ruler here, or if I take my, in this case I've got a tape measure. Let's flip it around so you guys can actually see the right way around. So I'm measuring this at almost exactly 10 centimeters, all right? That's 100 millimeters is what I'm measuring it at there. Now, that's one tool, and this tool works quite well, but there's more accurate tools out here. What I've got here is this is a digital caliper, and a digital caliper has the ability to go down to 100th of a millimeter. So if I span this guy out, and I measure from end to end, all right, and I get, when I just get it touching, boom, I get 100.39, okay, 100.3940, somewhere around there as my measurement of my wallet. Now, it would make zero sense if I were using my tape measure to report it as 0.39, because this guy cannot go that accurate, whereas this caliper can. And so we have these extra digits on the end because this digital caliper is accurate up to 100th of a millimeter. This can only go up to the nearest millimeter. So the accuracy of the tool is important. It would make no sense if I used this ruler to report the width of this wallet as 100.39 millimeters, because this guy is not that accurate. And so that's why significant digits are important. So this number of significant digits increase as the sensitivity of the measuring device increases. So let's try a couple examples. So let's look at that last example that we just did with the tape measure and the caliper. What we've got here is the tape measure we measured at 100 millimeters. That was the most detailed we could get on it, 100 millimeters. The caliper we measured at 100.39. Now, when we talk about significant digits, here's what we're doing. We are going to count, when we determine the number of significant digits, we're going to count from the first non-zero and then count every following number or zero. So I start here. Let's start with the tape measure first. I'm going to start here at that 1, and I'm going to count 1, 2, 3. So this guy here has 3 significant digits. Now, when we go count down here, we start at the first non-zero. That's 1, 2, 3, 4, 5. This guy has 5 significant digits. What that means is that this tool here was a much more accurate tool than what we used before. All right. Now let's look at a couple more examples, and what we'll do is we'll just count. We'll count each significant digit. So we're going to start from the first one here. We're going to start at this 358. So we start from the first non-zero. Okay, so this is a non-zero here. We're going to count 1, 2, 3. This guy here has 3 significant digits. Okay, next one, we're going to start from the first non-zero, and we're going to count 1, 2. This has 2 significant digits. All right, next one up, we're going to start from the first non-zero here. We're going to start here. We're going to count. Okay, we've got 1, 2, 3. 3 significant digits. You guys start to get the point. Now, what happens when a decimal gets involved here? Okay, so let's move this down so we get a little bit more separation here. Ooh, that's moving that one down. I just want to move this guy. Oh well. We start from the first non-zero here. We count 1, 2, 3. Even with this decimal here, this is our third one. So this guy here has 3 significant digits. What about this guy here? We start with our first non-zero. Here we go. We count 1, and we count all the zeros after it. 1, 2, 3. okay? And even this one after, we count 4. This guy here has 4 significant digits. Now, here's the first one where we don't have a non-zero as our starting point. So we've got 0, 0, 0. We're going to skip all of those and start with our first non-zero digit. So 1, 2, 3. This guy has 3 significant digits. Same with this guy. We're going to skip, skip, skip. None of those because they're all zeros we're going to start with. So there we've just got, this guy here is just this guy, which is just 1 significant digit. All right? That's how we determine the number of significant digits. So here's what I want you to do. We're going to practice a few of these. So at each one we're going to pause and I'm going to let you figure out how many significant digits this has, and then we'll check it together. So ready? We're going to start with this guy here. Okay, we're going to start with this 400. Ready? Go. How many significant digits? All right, so we have here's our first one. There's 1, 2, 3. This guy here has 3 significant digits. All right, let's move on to this one here. Let's move on to 320. All right, ready? Go. All right, so if you counted, this one would have had 1, 2, 3 significant digits. Okay, let's go on to the next one here, 200.0. Ready, go. All right, 1, 2, 3, 4. This guy here has 4 significant digits. Next one, we're going here to the 0.00530. All right, ready? We start here, go. We don't include any of these ones because it starts with a 0. We go to the next one, we go 1, 2, and this 0 afterwards is important. If they've included it, it's an important one. It meant that our device had that level of accuracy. So we go 1, 2, 3. This guy here has 3 significant digits. Okay, next one. All right, so 1, 2, 3. We don't include any of those because they're all leading zeros. We just have this guy here, which means this guy has 1 significant digit. You're starting to get the picture, right? Let's go to this guy here. Take a guess on this one. All right, so we've got 1, 2, 3, 4, 5. This is 5 significant digits. We also call this significant figures. We'll call it significant digits for our purposes. But okay, next one here, this 218, go. All right, here we go. Let's try it. Ready? 1, 2, 3. 3 significant digits. Wonderful. All right, and then our final one here, this big guy here. How many significant digits does this guy have? Ready? Go. Okay, we got 1, 2, 3, 4, 5, 6. This 0 matters at the end. So we've got 6 significant digits. Ooh, you can't really see that here. Let me just shift this over here so you guys can see. Nope. There we go. All right, so 6 significant figures. So that's how we determine the number of significant figures that are present in each one. So let's start talking about where we're going to use this. So when we're doing any type of calculations, what we're looking for is we can only go to the number of significant digits that is our least accurate measurement. So the smallest number of significant digits is what determines what our answer is going to be. So let me show you what I mean by that. Here I've got this simple multiplication. I've got 3.60 times 5.6, and that equals 20.16. Now, this in itself is fine, but here's our problem. If we treated these like measurements, and we had one that was measured up to 2 significant digits, let's count our significant digits first here. So we have 1, 2, 3. So this guy here is 3 significant digits, and this guy here is 1, 2. This is 2 significant digits. We're expressing the final answer right now with 1, 2, 3, 4 significant digits, right? And we don't have that level of accuracy. And so we need to go to the level of accuracy as our lowest number of significant digits. So we have 3 significant digits here, 2 significant digits here, which means that I need to express my answer to 2 significant digits. That's my smallest number of significant digits. All right? So this is really important. So our final answer, when we express our final answer, our final answer is going to be expressed as 2, 0. All right, and now that's already here, 1, 2 significant digits. So we're gonna express it as just 20. Now, how did I choose 20 versus other things? Well, I'm looking, and do I need to round? So this 1 here tells me that I'm gonna stay rounded down. Now, there's one more thing we need to talk about before we get into more examples. We need to talk about scientific notation. Now, scientific notation is a way of writing really, really big numbers. And not just big numbers, you could write any number with scientific notation, but specifically for really, really big numbers. So I want to show you 2 examples of how that works. We've talked about scientific notation in the past when we talked about Avogadro's number, and we talked about how that was 6.02 times 10 to the power of 23, and we've talked about how when we wrote it all out, it was 602 hexillion was the number we were talking about, a really big number written in a much smaller format. So here's what I want to do. I want to show you guys a couple of examples. Let's start with this first one here. If I had 104, that's my number, 104, and I wanted to express that in scientific notation. Here's the thing about scientific notation. You can only have a digit in the ones place. Okay, you can have all the other ones after tenths, hundredths, thousandths, and so on. But on the left-hand side of the decimal, so here's our decimal place here, you can only have a digit here in that one place. So if we were expressing this guy here, 104, in scientific notation, we would write that as 1.04 times 10 to the power of, and then we count how many times our point jumps. So in this case, it counts 1, 2, it jumps to get to our number. We would write it as 1.04 times 10 to the power of 2. All right, let's do another one here. This is 99,960. All right, if we wanted to write this as scientific notation, here's where our decimal place is here. We're going to jump over 1, 2, 3, 4 decimal places. So we would write that as 9.9960 times 10 to the power of 4. All right, we test this when we jump. When we jump over, we jump 1, 2, 3, 4, and that gives us our answer. So that's what determines what our exponent is. Now, one more thing that's worth talking about. If we had to write these numbers up to a specific number of significant digits, so let's call this here, let's say we're going to write these into the nearest 2 significant digits, all right? We can still keep this as scientific notation, all right? It's really hard to write 104 to 2 decimal places, all right? Because there's nothing really you can take out, so you have to write it as scientific notation. So if we were to write this as 2 significant digits scientific notation, we would write it as 1 point. And now this 4 is going to tell us whether we round up or round down. So it's going to tell us to stay down at 0. 1.0 times 10 to the power of 2. This is our nearest 2 significant digits. All right. We count them out here. We count 1, 2. There is our 2 significant digits. That's how we write it. So let's try this next example. We've got to get this number 99,960 to 2 significant digits, all right? 2 significant digits, and chances are we're probably going to have to write this in scientific notation because we can't express this number to 2 significant digits and still have it be 99,960. So to do that, let's just write that number out again. Let's write 99,960. All right? We know that we need to reference it to the nearest 2 significant digits. So we need to round here, and this guy here is going to tell us where to round. So it's going to tell us to round up. So when we round up, what we round up and what we get is we get something like this. All right? We get 100,000. And so if we were to write this as scientific notation, we count 1, 2, 3, 4, 5, we would end up writing this to 2 significant digits as, to 2 significant digits as 1.0 times 10 to the power of 5. All right? So we had to do some rounding in there to get it to 2 significant digits. The other way we could approach that with our same thing. So let's just move this out of the way for right now. Okay, so we could approach it the same way as if we had scientific notation, 9.9 times 10 to the power of 4. Now, this isn't a great one because this isn't rounded, right? There's another 9 here that's telling us what to do. So we're going to take this guy. It's going to tell us to round up. This is going to take it to 10.0 times 10 to the power of 4. If we move our decimal place over one more spot, we get 1.0 times 10 to the power of 5. Both those numbers are the exact same thing. So let's try a couple examples here. Let's try a couple examples, and what we'll do, the first two we'll do together, and then the ones after that you're going to try. We'll pause the video, you'll try it, we'll go through the answer together, and we'll cut you free from there. So let's start with this guy here. So here I've got 6 examples that we're going to go through together as a group. So let's start with this first one here. Let's start with this guy number 1 here. All right, so we've got 7.6 times 21.9. So let's punch that into our calculator really quick. So 7.6 times 21.9, that gives us 166.44. So 100, I'm just going to put this down here, 166.44. There we go. All right, 166.44. So now what we have to do is we have to count the number of significant digits that were present in our problem. So this guy here has 2 significant digits. This guy here has 3 significant digits. And so we need to express this answer to 2 significant digits. All right, so this guy expressed to 2 significant digits. Well, we're going to have to do scientific notation. So it's going to be 1.7, because I rounded this guy up here, 1.7 times 10 to the power of, we move this over 2 spots, 10 to the power of 2. There's my answer. All right, let's go on to this guy here. We're on to number 2 now. All right, so number 2. So we're going to punch this into our calculator. So let's go over to our calculator. We're going to clear this here. So we're going 2.15 times 3.1 times 100. That gives me an answer. I'm going to write this in down here. Okay, an answer for number 2 of 666.5. 666.5. Did I punch that in right? 2.15, 3.1 times 100. Beautiful. Okay, so there's my answer there. It's on there as number 2. We need to write that to the appropriate number of significant digits. So I have 3 significant digits here, I have 2 significant digits here, and I have 3 significant digits here. So I need to write it to 2 significant digits. That's my smallest number of significant digits in the problem. And so here's my 2 significant digits here. This guy is going to tell me to round up, and so I am going to get 6.7 times 10 to the power of, I move this over 2, 10 to the power of 2. There's my answer. All right, so we're going to move on to number 3 together. So here it is. So this is number 3 right here. Go ahead and try that one now. Go. All right, so here we've got, I'm going to punch this into my calculator. Here we go. So I did 5.0000409 times 0.06. And that equals, there's my answer there, 0.3000054. All right, so there's my answer there. Now let's count our number of significant digits. This has 1, 2, 3, 4, 5, 6. This has 6 significant digits. This guy, remember, these two don't count. We just have 1 significant digit. So we've got to express this to the nearest 1. So here's our nearest 1. This is what's going to go into our 1's place. It's going to be 3. And that significant digit is going to slide over there. So we would go 3 times 10 to the power of, now we moved it 1 to the right, so we would say -1. If I were to punch this in on a calculator here, let's go clear. And if I would go 3 times 10 to the power of, where's my negative button on this one, -1, I would get 0.03. That's exactly what we want. That's up to our nearest significant digit. So that one worked. All right, let's try number 4 together. We've got up here number 4. We've got 38 divided by 7. Ready? Pausing video now, give it a try. All right, so we're gonna do this one here. We're gonna do it on our calculator. So here's our calculator. We're going 38 divided by 7. That gives me an answer of 5.428 dot, 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 so many more numbers, all right? We need to express this to the appropriate number of significant digits. Now, we count here. We've got 2 significant digits here. We've got 1 significant digit here. So we need to express it to 1 significant digit. So we're going to write this as 5.4. This 4 is going to tell us we're just going to stay here. So I'm just going to write this as 5. That there is my final answer, the appropriate number of significant digits. I rounded. This is the one thing I've got. It's to 1 significant digit. So there's my answer there. All right, let's do these next 2 real fast here. I'm just going to get rid of these guys here. All right, so let's try number 5. Here you go. Ready? Go. All right, so I punched that into my calculator. Here's my calculator here. And so what I got was this number, 29,412.29412. So 29,412.29412. All right, so there's my answer there. Now I want to express this to the appropriate number of significant digits. So I'm going to count. This first number here has 1, 2, 3, 4, 5, 6 significant digits. This guy here has 1, 2, and all our zeros after are significant. So we count 1, 2, 3, so that's 5. Total 5 significant digits. So I need to express this thing to 5 significant digits. So I can write 1, 2, 3, 4, 5. There's my 5 significant digits there. This number here is going to tell me that I'm going to stay rounded down. All right, that 2 there. And so I could write this in 2 ways. I could write this as 29412. Done. There's my answer, 29,412. Or I could write this as 2.9412. Remember, this is still 5 significant digits. So 1, 2, 3, 4, 5 significant digits. All right. And I would write this, times 10 to the power of 1, 2, 3, 4. 1, 2, 3, 4 times 10 to the power of 4. So that's the other way I could write this one. Done. All right, let's go on to the next one here, our final one, number 6. Here we go. Ready, go. All right, so we'll come back over to the calculator here. We'll punch this in. So we have 5 followed by 5 zeros, 1, 2, 3, 4, 5. So that's 500,000 divided by 5.002. Punch that into the calculator. Oops. Delete. Enter. And so we get 99,960 point something. So let me just write that out. 960.01599. All right, there's my number there. So show you guys that. All right, now we need to put this in the appropriate number of significant digits. So here's my significant digits. I have 1, 2, 3, 4, 5, 6. This has 6 significant digits. 1, 2, 3, 4. This has 4 significant digits. All right, so let's count here. We got to go to the nearest 4 significant digits. 1, 2, 3, 4. So we're going to write it in scientific notation for sure. We're going to write it as 9.996 times 10 to the power of 1, 2, 3, 4 times 10 to the power of 4. Now this guy here, this number right here tells me whether I need to round this guy. All right, and because this is low, we can keep that exactly the same. We don't have to round up. So here's my final answer for that guy. 9.996 times 10 to the power of 4. We have 4 significant digits right here that determine our final thing. So hopefully this has been helpful for you. From here on out, with all of the math that we're going to be doing in class, you need to express this in scientific, or you need to express your answers to the appropriate number of scientific or significant digits. Accuracy matters in this case. So that's all for this lesson. We'll start this thing off again tomorrow when we start talking about work. Bye.